The last presentation before lunch is from Erik Peters from Alert Solution about the famous GeoBeat.
Dank u. Geef jij de presentatie? I was very happy to welcome many of you yesterday morning, early in the morning, 8:15, outside on the Stammerdijk nearby Amsterdam. That was quite a cold venue, so we had the presentation on the bus, but managed to step out on the dike for a moment as well, looking at some live data. Well, I had a very small screen for the presentation in the bus. At least now I have a bigger screen, so I'll redo part of the presentation, but I'll focus on some different things as well. Alert Solutions is the company that I founded in 2007, and GeoBeats is the product that we developed. Sometimes there's a question, is GeoBeats synonymous with Alert Solutions? Yes, they're basically one thing, because GeoBeats is currently the only product line we carry. The trigger for starting this company was some of the flood events that we had in 2003 and 2005 here in Holland, and then also the early stage of the Eikdijk program, which gave companies a physical test field to test these new developments, so making it a lot easier to actually put your developments into practice. I consistently use the word levee instead of dike when I speak in English. It's probably because of my American schooling. I guess in the US they mostly call them levees. Okay, presentation agenda. I'm going to talk briefly about the GeoBeat system. It is, of course, in this theme the main topic. The applications we put in levee monitoring, and how do we support some of the objectives that water boards have with monitoring. And I'd like to make a link to the urban flood project as well, and maybe trigger some of your thoughts. Okay, this is the core of the GeoBeats product, and I think we did something that is quite evident and simple, but not so easy to put into practice. I'm happy that temperature was mentioned in the last presentation as an important parameter, because we aim to put all vital parameters together into a single sensor module, so that each measurement location measures all your needed parameters for ground stability monitoring, and that you can also correlate these parameters because you have them at the exact same location. In order to make this a scalable thing, so an array of measurement points, instead of wiring all these sensor elements to the surface and digitizing them there, we digitize them directly onto the electronics platform that we designed for this. So what is usually called a data logger is included in each sensor module, reading out the sensors, inserting the calibration coefficients, temperature compensation, and transmitting messages out with a timestamp and a location information, a unique ID, on somewhat of an IP-based addressable network bus, making this an infinitely scalable network configuration. So we have some small units at the top of the levee for wireless transmission or wire transmission, but basically IP-based protocol comes straight out of the levee, making it very easy to plug into ICT systems. So at the Eikdijk we had just an Ethernet cable running off the levee to run the data of 50 of these modules spread throughout the dike and the ground layers at an interval of once per minute, but once per second can be handled. Also important for field deployment is that you have energy saving mode, so that you can run them on battery power, because we often install in remote areas. So here's a picture of how we drew our vision of instrumenting a levee before we did any of the development. We wanted to make it a flexibly installable network, both in vertical sense to monitor different ground layers, but in any direction, and the scalability should take care of that. Well, in practice, we mostly install vertically because you want to do the least amount of damage to your existing levee structures. So this is the setup of a cross-section of the STOWA dike where we were, and the locations of the geobeats in different ground layers, and from the water side to the land side. And that is a very typical setup, and then a repetition of these cross-sections in the length of the levee. So putting it into practice, well, we measure 3 different parameters. We want to measure them all reliably, and that is sometimes somewhat contradictory. Pore pressures are the main parameter going into stability models, and you mentioned swell gel. We use swell clay, a natural material, around the cable to isolate different levels, different ground layers, so that in a single installation stroke, a pushing of this string into the levee in a vertical manner, you can install multiple levels. We install them directly into the ground to have optimal contact and embedding into the ground layers. Also for the temperature measurement. Modules, I have one on display on the table in the coffee room. They're quite small. They're 22 millimeters in diameter, so less than an inch, so that they can also fit in standard standpipes. And about 20 centimeters in length. And we install them always with standard geotechnical installation equipment, either by drilling, but we avoid drilling because you take out material, you disturb your ground. So mostly we push them up in with sounding rigs. Well, because we use standard equipment, we basically can go anywhere in the world for this installation, and train a local company to install it. Well, this is putting the instrument in practice, but of course here we're mostly interested in the data. And as I said, we bring these sensor networks real-time online. We have on the STOWA dike a GSM GPRS relay, so an IP-based connection. Transmit that to our central data server, but from there on, this data is immediately streamed through to the urban flood server, for example. So this data is available there. This is an example of our online data panel, so that we can view from anywhere the data live, in a live manner. And this is an example of the famous Ike dike, where we had this configuration. And here you see some inclination measurements in the peat layers, also about 48, 52 hours before the dike collapsed. So we believe we've brought together quite a unique set of features based on common electronics principles, but by bringing them together, we created an effective monitoring array, multi-sensor, networked, live access, and low cost of ownership, and also because of the long lifetime we're achieving with these instruments on all parameters. The company only exists for 3.5 years now, so that's the length of our track record. Systems are performing well. We've designed them to last over 10 years. And are confident that we reach that on average. We continue development on this because of course we started with prototypes in the Ike dike. We're now putting them in practice. We learn a lot from that, and our ambition in our development roadmap, and this, these are all in our mind realistic targets, is that we provide pore water pressure at 0.01% of full scale. That means in practice with our mostly used sensor, we should be able to detect 0.25 millibars of change, or 2.5 millimeters of water level change. And why do we want that accuracy? Want that accuracy to have the earliest detection of a significant change, so that you can track back where did it initiate and what were the circumstances. The same holds down to temperature. We can already, and I have shown that in the AgDike, get a resolution of 0.01 of a degree change. Of course, the absolute calibration accuracy is somewhat harder with temperature, and we reach about 0.1 of a degree, but it's the temperature changes that you want. Same holds for inclination. We re-zero them after installation, and then changes of 0.01 of a degree with respect to the gravitational field can be detected. In the future, we think there are some other relevant parameters. The platform is set up in such a way that we can add many more sensors to this sensor node in the same module. And what we're thinking about is absolute displacement. That's mostly a mechanical change of the enclosure, so that it is installed in a more rigid array, so we can translate inclination to absolute displacements in sub-millimeter range. Soil moisture above your groundwater level says something about the weight of your levee, and salinity is an increasing problem here in Holland with the subsiding of the land and the rising of the sea level. Also, we aim to increase the energy efficiency of the entire system so that it is more easily rolled out to any location. We want to run a typical levee network of about 20 of these sensor modules and one transmission module on a single D-cell battery for a number of years at a transmission frequency of once per hour. And we aim to increase the ease of use by making stronger visualization software available, but also to include any of the developed models. So we're very interested in cooperating with all those people working on models, because we'd like to actually make them available to our users as well once they reach maturity. Okay, our track record so far. Of course, we were present in all the AgDike levee experiments. One on macro stability, and we were in 2 of the piping levees. All 3 parameters showed significance in detecting and predicting the dike failure. Poor water pressure being the most direct as a cause, and deformation as being the most prominent as an effect and a signaling that failure would take place. Since then, we've instrumented the 9 existing levee sites in Holland. That includes the live dike at the Eemshaven harbor in the north of the Netherlands, from which you, I think, also received the data. At the Urban Flood Project through a live link. Several primary river levees and several regional and urban peat levees, and those are the focus area of the Dutch flood defense system. Besides levees, we're also active in France on mountainous landslide sites, both in coastal region in Normandy and the Alps. We've instrumented 2 urban construction sites, so around building pits for ground stability, both in the ground and against building facades. And we're now involved in monitoring one underground energy storage system here in Holland, where they pump hot water into the aquifer layers, and we want to see the effect on fresh or on drinking water wells in the area. Okay, I'm going to go quickly through 2 case examples. One of a major river levee. It's called the lekdijk, which is kind of has a double meaning in Dutch, because lek means leakage and dike means dike. So it's in its name it's already the leaking dike. But and in practice it holds true to its name. But most Here we see the area. This is the Rotterdam area with the largest port of Europe there. It's one of the rivers feeding into that port area. Here we see the outside of the levee. It is under tidal influence, so we have quite a lot of river water changes, even though it's about 50 kilometers from the shore. And this is the backside of the levee, the land side, and there's a lot of housing historically been built up both behind and on the levee. And this is where we are installing. The major risks here are heave, or maybe we should call it uplift. So the water pressure from the river goes to the lower layers and gives an upwards pressure here behind the levee. That can lead to a lowering of the stability of the dike, or when it bursts open, it can form piping wells, undermining the levee as well. So before we put a network of sensors in, we sit down with the geotechnical involved people and to see, okay, how do we assess these risks, and in what positions should we put the sensors to best get relevant data. So there's a lot of going back to the historic research of ground layers. Here you can see this is a length profile, so you can see it's a very inhomogeneous levee, and this is a cross-sectional profile. There's a lot of different layers throughout the centuries. Sand layers, soft peat layers, and we want to see the effect of pressure in the sand layer into the peat layers. Is there an uplift effect or not? And this is the actual measurements then from 9 different levels in the ground. We can see the lower 3 levels, the sand layer, but also the lower peat layers, have the tidal influence. And through that we can also see the influence of the river level over a long period. It works directly into these lower layers, but it's dampened out with the higher layers. And this can be a direct input to the stability model being used to audit this levee. And this levee is on nomination for a reinforcement, which would cost for this levee anywhere between 2 and 5 million euros per stretching kilometer. And with this study we aim to either see if that was a correct conclusion, or sharpen the reinforcement design, thereby lowering the cost of the reinforcement. We also take into account meteorological inputs, so external data sources, and we're looking at early detection of movement. At what pressure buildup here do we actually see movement in the ground layers, as a sort of threshold setting for when it comes close to failure, and thereby becoming an early warning system. This is the levee we visited yesterday, the Stammer Dijk. The urban flood levee. Well, I put urban in parentheses because it's quite a nice pasture here with the horses that came to visit us at the fence yesterday as well. But you can see it's quite close. Amsterdam starts right here, big hotel here, highways around it. So I think we can call it an urban area. Well, we started monitoring this levee for the water board, and then added the urban flood objectives to it. The water board is also reassessing this levee due to the last auditing round of the levees, which would also, well, it's somewhat at the border of needing a reinforcement. So we're doing several experiments to actually quantify effects that this levee is changing, instead of basing the audit on assumed uncertainty margins or safety margins. And this was a traffic loading with this truck of water net that we did last week. This is the effect on inclination in several areas, and we drove the truck back and forth a bit to see how fast the response was, but also the elasticity of the levee. And we saw this in several pore water pressures as well. So valuable data, I believe, for WaterNet to do their reassessment of this levee stretch, and to be also a reference levee for other such levees in the area. come to my concluding slide, because I also want to, as I said before, trigger your thoughts. We currently have two GeoBeats networks that provide urban flood data, quite different levees. I think there is different potential failure mechanisms, different build-up, so there's already quite an interesting comparison of data that can come from this this database. So if we look from we mostly do analysis in time trends, in the ground mechanical models, etc. But if we look beyond that and to scalable systems, we've done little work so far really to look at the correlation between the different parameters, the comparison of different levees. Do we see a temporal and spatial, so 4D trend behavior, and can we interpolate to areas that we have not instrumented, or extrapolate to areas we have not instrumented, and also say clever things about that. Statistical modeling and change point relevance. When does a change in your data actually mean something is happening? And of course, working towards prediction models. To come, I think, in the end, for the community, to the definition of an early warning system using both sensing and intelligent data processing. We're interested to be part of that effort and to expand to international sites to increase our knowledge as well. Thank you for your attention.
Okay, thank you, Erik. Any questions? Rob?
Small remark. So every time there's a tide effect in the leg, in the future we will test the dike. Yeah? So the tides are a continuous signal on the dike, and in the future you will continuously check if the response is the same as yesterday.
That's true. For such a project, it's very nice to be in a tidal region, because you get a continuous source to measure the response to changing river levels. So you can already correlate between your pressures in the levee and the outside water level, and start building up that correlation every day in a more accurate manner. And of course, one trigger can be when you start leaving that correlation. Maybe something changed in your levee, but you have a continuous build-up of this correlation. So you don't have to wait for higher waters.
So the same as with the truck. Every time a truck will drive over a dike or a ship will pass along it, you have a test.
Okay.
So we only have the challenge to identify those events as well.
Okay, Wouter.
I am Wouter Zomer, Managing Director of the Eikdijk Foundation, and I'd like to start with thanking the speakers of this morning for mentioning the Eikdijk so many times. Free publicity, thank you. And a question I ask Erik, but also the other speakers. The main platform for sharing data is called Internet, but what if Internet fails in case of a calamity, or data cannot be transmitted, or these things? What then?
No. Just a second. The question was also to other speakers. So, Patrick.
Indeed, this is a great vulnerability, according to our analysis with most of the systems which were presented. But this is why we focus on a totally passive sensor, which is the optical fiber. Our system, in fact, all the data are gathered on a room, which is of course safe in case of flood and so on, and which is self-powered as well. And therefore, in case of flood or any kind of event like this, our system is still going in progress. Totally independent. And for instance, in one of the rivers to the south of France, we are presently asking the authorities to have access to a given electromagnetic band, so that even if there is a problem, we have access to this given electromagnetic band, for security reasons. And therefore our system, and according to me this is the main advantage, is that it is totally independent and will not be affected by this, as well as another vulnerability. It is the fact that when you're installing many equipments on a dike, people who are, well, I don't know whether it's the case here in Holland, but if in France you have anything which can be seen on a dike, somebody will dig and say, what is it? And they will destroy it. And this is why our system is digged within the dike. Nobody sees anything but a house, which of course is secured. And this is our main purpose, and this is, according to me, the main advantage.
I think Rob also wants to comment on the question of what happens when the internet fails.
Yeah. Yeah, I think this morning I received a few emails, and now I'm receiving a few emails. So let's say in the more urban side of the internet, I have no worry. So the only worry is in the vicinity of the dikes. Yeah? So there we have to maybe use internet technology, but the engineering of a connection between well-maintained internet, yeah, like the public internet, to the dike, that is a matter of dedicated engineering. You will use the internet technology for it, but of course the cable, the connection, most probably will be of the dike owner. And then of course buried systems and wireless systems are less prone, but you will still call that internet, but it is a matter of engineering. Any telecommunication operator who says that he can be, everybody who can say we can generate a more stable network than the internet or the public networks, I would doubt. Okay.
Okay, one more question before lunch, or I will, André.
Erik, you wanted to increase your accuracy on pore pressure measurements to what level exactly?
Right, you divide the millibars by a factor of 10, so that's 0.025 kPAs. Corresponding to 2.5 millimeters of water column. That's the resolution of change detection that we want to achieve. Of course, often your uncertainty about at which depth you're actually located, because you measure them by GPS, which often gives an accuracy of about 3 centimeters with respect to a grass-covered surface, which is rough as well. So your installation accuracy is often less, which determines your absolute value accuracy. But we want to be able to accurately and reproducibly measure changes of several millimeters of water.
Well, I've been involved with the piping experiments and with pore pressure measurements. You're able to detect piping in a very early stage, but then you really do require that accuracy Erik is aiming at, not for the absolute value, but relative values, the difference between the present value and the previous measurement. So your aim is also the threshold value for detection. It should not be, it's really the accuracy you need for piping detection.
I knew that, so you have told me before, and I'm happy to say that we have this running in the lab already as a prototype. So we're able to reach that accuracy. We want to make sure that it reproduces in the data flow. So, but we'll be releasing it early 2011.
Okay, thanks again, Erik.